The theory group here, and it's with great pleasure that I welcome you to Carlo Condalti's inaugural lecture. Carlo did his undergraduate here, and his PhD, and his MSc, I guess. Was it then called?
It was MSci.
MSci, okay. Then was a postdoc here?
No.
No? Okay. All I had was what it said. Then you went to CETA in Toronto for a postdoc, then came back here. And came in 2005. I have that right? Okay. So he's clearly like a product of Imperial. I was ever so slightly tempted to go and see what his undergraduate mark was, just to kind of check that we admitted the right person, but I think it's pretty clear we did. I'm not really going to say anything about your work because we're going to hear about it, but I will say that it's really been a great pleasure having him in the group, both intellectually and personally, and I'm very pleased to hear that he's going to give his inaugural and hear what he's going to say. So, Carlo.
Okay, well, thanks, Dan. Okay, so it's quite a surreal experience giving this kind of lecture in this lecture theatre because I remember it really sort of as clear as yesterday when I was standing about 3 rows down from the end there, and that was about 23 years ago when I was embarking on my what turned out to be a career as a physicist. That was day 1 of my undergraduate degree. It was quite daunting to give this kind of lecture because it's a very mixed crowd, colleagues and physicists and non-physicists and children, and hopefully, what I'd like you to take away from this lecture is really sort of a story about how the field I work in has been transformed incredibly over the past 20 years that I've been involved in it, and also the sort of sense of awe that I still have when I consider the kind of results and discoveries that have happened, and how lucky I've been to be involved with those. When I get asked what I do, let me just turn the lights down here a bit. Just especially for this slide. When I ask what I do, most of the time I explain I'm a cosmologist. What do we do as cosmologists? Well, we look at the universe, and I often show this picture because it sort of gives you a sense of the amazing things that are out there. Just to give you a feel for why we're curious to understand how the universe works and what it's made of. And this is a picture, it's called the Hubble Extreme Deep Field, and it's when they point the Hubble telescope, which has been up there for many years now, observing objects in the universe, and they point it on one single patch of the sky, and it just sits there and integrates for a very long time. I think this is probably the deepest integration that Hubble has carried out. And spending so much time in one single patch, it allows it to pick up even the faintest objects at the limit of its resolution. And it's quite a stunning picture. So you can probably see it better on that side, a projector there. Just to give you an idea of the scale of this patch, that's the size of the moon compared to this little patch here. Right? This is the extreme deep field. Okay, so this is the patch that we're going to focus on. This length here is a degree on the sky, so there are a huge number of these little patches to make up the whole area of the sky. So that gives you an idea of the scale that we're looking at. And this patch looks like this. There's lots of objects in there. It was chosen because there's very few foreground stars, and most of the objects you see here are galaxies, very distant galaxies. And the amazing thing is, if you zoom in to the picture, you see some clearly defined objects that obviously look like spiral galaxies, but every little dot of light here is a distant galaxy. That's amazing. This tiny area of the sky has thousands and thousands of objects at huge distances, okay, and there are there's a huge amount of structure out there over the sky. These extremely faint objects here are some of the most distant objects that have been imaged. They're at billions and billions of light years away, and each one of them, this is the mind-boggling fact, is a galaxy with billions of stars in it, millions and billions of stars, just like ours, okay? So there's an incredible amount of stuff out there. Of course, when you look at this kind of picture, what you're also seeing is you're seeing the universe at different times. Light travels at a finite speed, so as you look into the universe, more distant objects, you're seeing them at an earlier time. So this picture tells you something about the evolution of the universe. And as cosmologists, right, one of our main interests is to come up with a model that describes the universe and how it evolved in time. And of course, cosmology has been around for thousands of years, okay? The kind of questions we ask now were being asked by people thousands of years. There's a record going back to the first written manuscripts about cosmology, about what we thought the universe, how we thought it came into being, etc. But what I would define as modern cosmology started in the at the beginning of the 20th century, and the big developments then were the development of a theory of general relativity by this character here, very well-known physicist, Albert Einstein. And around the same time, a couple of decades later, Edwin Hubble made his famous discovery that what were understood to be nebulae or galaxies were actually moving away from us. So he looked out on the sky, those kind of objects I just showed you, and he measured the velocity at which they were receding away from us. This was really a paradigm shift in our understanding of the universe. It was common to think of the universe as a static and eternal entity until then, but this discovery meant that the universe was evolving, and in particular that space-time was expanding. Right? The universe was expanding, so this notion of an expanding and evolving universe became mainstream. And these objects were moving away from us, and the further away they were, the faster they were moving away, and that is known as Hubble's law. And this allowed us to start thinking about the big questions which had always been asked, but to start thinking about quantifying answers to these questions. So this using general relativity and using observations and combining those to build models of the universe which described what we saw. But the questions were the same. What is the origin of the universe? Where did it come from? How does it work? Okay, what are the physical laws that make the universe tick? How old is it? That's a very profound question. How long has it been around? And of course, we'd like to know what is going to happen to the universe. What is the ultimate fate of the universe? Okay, so these questions. We're at that stage. We're able to then start answering in a more precise way. You can think of. The model that we use to describe the universe, the most common model, is actually really simple, and I thought I'd spend a slide trying to give you a feeling for the ingredients of that model. It's a model where we just assume the universe is isotropic and homogeneous. Okay, so on average, the universe looks the same whether I look in that direction or this direction. And if I move to another region of the universe, it will just look very similar to the region I was in before. The geometry of the universe can be closed, flat, or open, and I'll mention that in a little bit more detail in a second. But the way we describe the evolution, this expansion, is very simple. The model has a scale factor that describes how the distance between typical observers or galaxy in the universe evolves in time. So if I'm sitting on a galaxy here and I observe other galaxies in the universe, and I have some way of measuring the distance between us, and I measure that distance after a very long time, I would notice that that distance has grown if the universe is expanding, and we describe that using this function a. And a is a function of time t. And the evolution of the universe, it's incredibly simple. It's described by how the scale factor evolves in time. This function here, this number, which we call the Hubble rate, which is related to the Hubble constant of the Hubble's law, that velocity of receding galaxies, just tells us how fast this scale factor is changing in time. Okay? And on top of that, there's sort of an acceleration of that scale factor, how h itself is changing in time. And I mention that specifically because acceleration is something that will, as you'll see, has some profound significance in modern cosmology. And then it's actually the evolution of the universe in time actually turns out to be quite simple if you make those assumptions. And this is basically the skeleton of a Big Bang model. Okay, the universe starts off. Well, we live in a universe which is expanding today. So this is a sort of a plot of cosmological time, right here on the bottom, and the scale factor, which you can think of a little bit like the size of the universe. And we start off here at early times, and we start off with a Big Bang. The way to think about this is that everything we see in the universe, the volume that we have access to, which is finite because of the finite speed of light, well, that entire region came from a very, very small region of space-time. And that is the Big Bang. And the universe, we see it's expanding today. So it expanded, we think it expanded from this Big Bang event, which happened everywhere. This is something which is very confusing to students when they first start thinking about the Big Bang. And the way it evolves forward, okay, is determined by how much matter there is in the universe, okay, how dense the universe is. And depending on whether the density of the universe, the stuff that makes up the universe, the matter in the universe, matter and energy, depending on how dense it is, okay, compared to a critical value, then the universe will have three possible, will evolve in three possible ways. One is that if the density is above a critical value, the universe will expand, it will reach a maximum, and then the scale factor will start decreasing. And the universe will end in some big crunch. And then there's other two possibilities. One is that somehow the density of the universe is just the right amount to be at this critical value. And then we call that a flat model, this blue curve here. And the universe keeps on expanding. And the same thing happens, the same eternal expansion happens if you have an open model. By that we mean that this density is below this critical value. So very few ingredients. Conceptually, it's a difficult thing to get your head around, I guess, but very few ingredients. And at the middle of the 20th century, this is how simple well, my job could have been if I'd been around then. Okay? Okay, everything's determined by the density of matter in the universe. And the matter in the universe is in the form of stars that sit in galaxies. Okay? That's what we see in that image, that Hubble image. So I need to determine the density of stuff in the universe. Well, I can imagine doing that by going out and counting the number of galaxies in pictures such as this. And then I sort of come up with a number that says, well, typically each galaxy has so many stars in it. Each star, well, roughly is sort of a solar mass. That gives me some value for the mass of each galaxy. And I multiply that by the density of galaxies I see in the sky. And then I compare that number, and I'll call this omega, to the critical value to obtain this factor omega. And then the conclusion could have been very simple, right? Based on this number here, omega, well, I could have told you, well, we live in a, open or flat or closed universe. The universe is full of matter. And by matter, I mean particles that we're all used to. They're part of the standard model, atoms and photons. And I'll call them baryons and photons. Baryons just means it's heavy stuff, heavy particles. And photons are, photons are massless. And we tend to just describe matter in the universe as baryons and photons, lumping everything together. And then I could have told you, well, the universe started with a Big Bang. Okay, that's the case because it's expanding now and it came from a Big Bang. And depending on the value of this parameter here, well, I could have told you, well, it'll end in, either expand forever at different rates, or it'll end in a big crunch. Okay, life could have been that simple. In fact, it didn't turn out to be that simple. It turned out to be a lot more interesting. And I refer here to a period which is 1996 because that's sort of the period when I became aware of cosmology as a subject. And at that time, really cool data was coming into the field. It was really becoming a field which was driven by data. And these were the sorts of things that were happening. Observers were going out and measuring, mapping the distribution of galaxies in the universe. So this is an old survey. These were called galaxy redshift surveys, or they're still called galaxy redshift surveys. But basically, you're mapping the universe, and each one of these dots is some galaxy. Very small distances away from us, so we're here, and this is sort of maps the structure around us. And even a simple map like this, a few thousand objects, gave cosmologists an idea of how structure was forming in the universe. Structure forms because under the action of gravity, matter clumps together and galaxies build up and then start forming clusters of galaxies and larger structures. And depending on how much structure there is, you can then fit that to some model of how the universe should evolve. The other thing that was happening was the Hubble Space Telescope, which I've already mentioned, was launched in the early 90s. It was a disaster initially. If some of you might remember, the lens was ground wrong. It was distorting the images, but they sent up a repair mission, and then Hubble started fulfilling its role, which is essentially to redo Hubble's work much more precisely and measure the rate of the expansion of the universe, this Hubble constant or Hubble rate. And then a hugely significant thing that happened is the CMB satellite, which measured the cosmic microwave background, and I'll come back to that later on. The work of the observations from this satellite confirmed it really underpinned the Big Bang model of cosmology. But there was strange things that were also obvious in the data. When looking at this picture, it became quite obvious that you couldn't explain the amount of structure that had formed in the lifetime of the universe just based on the amount of stuff you could see, the visible matter, right? Stuff that emitted light, the galaxies that you could see. And this was the dark matter problem. Okay, to explain this kind of structure, cosmologists needed to introduce a form of dark matter. And also, this problem had been around for a long time in all shapes and forms. One of the clearest indications that dark matter existed in some form was when people started looking at rotation velocities in galaxies. And when they looked at the dependence of the velocity of rotation as a function of radius away from the center of the galaxy, it was quite clear that what you could see, the visible part of the galaxy, couldn't explain the velocities that you were observing. Okay, and the only way to explain it was to say, actually, that galaxy, the mass contained in that galaxy extends far beyond what we can see in the visible. So this was one of the big problems of classical cosmology, is that we required this dark matter. Okay, it was stuff which didn't interact in an obvious way with a standard model. It didn't emit light, and it didn't scatter off standard model particles. It didn't interact with baryons and photons. Also, other classical problems with cosmology were that because of the finite speed of light, we know that causal horizons exist. I can only communicate with observers at a certain distance away from me if the signal they have sent to me has had time enough to reach me. That's basically the problem. And this had created profound problems in understanding why the universe was so homogeneous. If I thought of a region that was far out there, far out in the universe in that direction, and then I looked at another region in the completely opposite direction, at cosmological distances, far in the past, if the universe had always expanded in the way we thought it was expanding, then those regions could never have talked to each other. They would never have been in causal contact. And this created a problem. Why don't I see stuff very different over there from over there? Okay, and this is a problem of, it's known as the homogeneity problem. And another thing was that the density of the universe was very close to critical, at this critical value. They didn't quite know how close it was, but it was suspiciously close to 1. And that was very strange because if I set off the universe expanding and the density is critical, the density of the universe will evolve away from that critical value. And the universe is very old and big. And if something's wrong in your model and it's evolving away from what you see, the universe being so old means it's got a lot of time to become very different, right? So that was a big problem, and it's a problem of fine-tuning. So the emerging picture was that it wasn't as simple as you may have thought. The universe was made up by not just baryons and photons, but you have to add in what was then starting to emerge as a standard sort of cold dark matter form of matter and energy, which no one had really predicted. And another groundbreaking idea in the 1980s that emerged was the idea of acceleration. And if you added an initial, in the early universe, at the time of the Big Bang, a stage in which the universe accelerated for a very brief period of time, then you could actually solve these other classical problems of cosmology. You would drive the universe to this critical density value, and you'd set up your universe in a nice way that would then explain what we see today. And it would also explain things like the horizon problem and homogeneity. And that was known as the theory of inflation. But the CMB was the development that really underpins the Big Bang model, as I mentioned. The CMB was discovered in 1965, but it was actually predicted a few decades before. When people started thinking about, well, if the universe is this big today and it's been expanding, well, in the past, right, the stuff we see, the matter we see, well, the density was a lot larger, the temperature was much larger, and there will come a time, there was a time in the distant past when the universe was actually made up of a plasma. The CMB itself was discovered sort of by accident by Penzias and Wilson, who were surveying the sky at microwave frequencies, and what they found was some completely isotropic signal that came from all directions in the sky. And the importance of this discovery was realized by colleagues at Princeton who related it to what had been predicted as a primordial fireball. Okay, what is this? Let me try and give you a sort of sketch out why the CMB, how the CMB formed. The cosmic microwave background is made up of photons, and you can think of them as the oldest photons in the universe. They're a relic photons. And they are photons that last interacted with matter, with the rest of the matter in the universe, when the universe was very young, at an age about 400,000 years after the Big Bang. This radiation fills the universe, it's everywhere. And this is a sort of a cartoon version of the evolution of the universe, which you sort of see quite often today. The universe starts off at a Big Bang. This is a completely wrong picture to think, but it's a sort of quite a common picture to draw now. It makes you think the Big Bang happened as a white fuzzy ball at a precise point in space-time. I guess it's the only way you could really draw it. Shortly after, the universe undergoes this inflation, this period of inflation, and there, just think acceleration. I'm going to come back to acceleration a couple of times. And that happens in the tiniest fractions of a second after the Big Bang. The universe then stops this accelerated expansion and then just enters what we think of as the standard Big Bang phase, which is just it starts expanding, and the expansion is decelerating. And up to a few seconds after the Big Bang, around about a few seconds into it, we understand exactly what's going on. Our physics models of physics for that at those energies are quite robust. We understand how light elements formed at that time. Things like light elements like hydrogen and helium formed, and then nothing much happens after between a few minutes and this epoch, which is at 400,000 years after the Big Bang. But the universe is in a very interesting state. At that stage, it's so hot and dense that the hydrogen is ionized, and you can think of the universe as a soup made up of hydrogen nuclei, electrons which are scattering off these nuclei but are essentially free, and photons. Because the plasma is this is a plasma, it's an ionized gas, the photon sees the electron charges whizzing around and they scatter off these electrons. Okay? The result of that is that the photons travel very tiny, infinitesimally small paths in between scattering. The mean free path of the photon is vanishingly small. And this means that the universe is actually opaque. Okay? Photons can't travel through this plasma. So the universe is opaque. Photons are scattering off the baryons, the hydrogen, and everything's coupled together. And we call this the photon-baryon fluid. It's like a soup, and the photons are sloshing around with the rest of the matter. Dark matter is there, but it's doing its own thing. It decoupled at much earlier time scales, and it's driving the formation of structure. So there is structure forming all the time in the universe here. And then as the universe expands and cools, the temperature drops below threshold when the electrons can recombine with the hydrogen nuclei and form neutral hydrogen. When the gas becomes neutral, the photons stop interacting with the rest of the matter. And this happens quite quickly on cosmological timescales. And from that moment on, these photons are free to just travel through the universe without scattering ever again. Typically, they just won't scatter. Most of them will not scatter against matter ever again. The only thing that happens to this radiation as it just moves away from this surface of last scattering, as we tend to call it, is that it gets redshifted by the expansion of the universe. So it starts off at a few thousand Kelvin as a black body radiation with a black body temperature of 3,000 Kelvin, but the subsequent expansion of the universe cools it down to about 2.7 Kelvin. And we observe it today at frequencies of around 100 gigahertz, centimeter wavelengths. And this is another analogy that is useful to think about. We sit here and we look around us, and we see at a certain distance from us, which is the surface that at 400,000 years after the Big Bang, that we see as a sphere around us, the CMB, there's this last scattering surface, and we can think of that as the CMB photons coming from that surface. And the analogy is like when you look up into the sky and see on a cloudy day, and you see the base of the clouds. And you can think of, well, the base of the clouds is where the photons last scattered with the water molecules in the cloud, and so I can see a surface. And the interesting thing about that surface is that it actually carries information about that cloud it left, that region that it left, and we can see that as structure in clouds. Okay? The same exact thing happens with CMB photons. And in fact, there was a prediction that you would see structure, we call anisotropies, in the cosmic microwave background. And NASA built the COBE satellite to go on and try and discover these anisotropies. It was a huge effort. And they were discovered in 1992. So here you see a map of the sky. This is the whole celestial sphere. And if you look at, if you take a survey in the microwave, you'll see a completely isotropic signal that you can interpret as a black body at 2.7 Kelvin. But if you are sensitive enough to see things, fluctuations in the temperature coming from different directions in the sky at the level of microkelvin, and you can subtract out the average value that you see over the entire sky, you'll see a picture like this on the sky. This is a map of the anisotropies as seen by COBE. The color scale here shows you tiny temperature fluctuations around the mean. So the sky is colder or warmer in different directions. The largest feature you see here is the galaxy, because the galaxy does emit in the microwave. It's a foreground that obscures the CMB. This was a huge result. It confirmed the nature of this blackbody radiation, because it measured the incredible blackbody spectrum of this radiation, and it measured anisotropies. What you see here, rather here in a picture where they fit out the galaxy, is a snapshot of the structure that was present in the early universe at 400,000 years just after the Big Bang. And it's an incredible picture. It's like taking a picture of the universe, of the young universe. This is another view of it. Again, sometimes people find it hard to visualize this, but this is a map of the entire sky, just like a map of the Earth, except what you're actually mapping is a celestial sphere. And you can see here these fluctuations. How do we compress information on this? When I was told to prepare this talk, I said, they told me, never show a plot in this kind of talk. I have to show a plot because this is a plot I've been staring at for the past, 20 years. So I couldn't get away without trying to explain what this means. This is a power spectrum. And the way to think about it, if you've never done this, is remember the old stereos? When you listen to music, I haven't seen it for ages now, but big clunky thing, and there'd be a display on there, and it would display the spectrum of the sound of the music you were playing. And all that was doing was breaking down the sound into frequency bins and telling you how much power was being output at each frequency, okay? When we take a map of the sky, the CMB, we do the same exact thing, but instead of working with frequencies, we split it up into spatial frequencies, which are related to scales on the sky. Okay? So this kind of plot, don't worry about the axes, but it's telling you how much structure there is on different angular scales in the sky. And this end here is large features on the sky, and you go towards small features on the sky. And COBE observed this region. It's observed on scales of around 10 degrees. These are these structures that you see in the COBE map on the scale of 10 degrees. And all I want you to sort of focus on is there is this line here. This is a theoretical prediction of how the power is distributed in that map. Okay? And it's got this sort of peaky structure here. And that arises because one of the things you see, not in the Kobe map, but we've since verified, is that this photon baryon fluid was undergoing acoustic oscillations. There were sound waves in the universe at that time. And when you took that snapshot of of the universe, when the photons left the last scattering surface, they carried information of those acoustic oscillations, those sound waves. So you can think of these as a little bit as the harmonics of these typical sound waves that were permeating the universe at that time. So just remember there's peaky stuff here. To the trained eye, this is 2 or 3 people that are experts in this. This is what you see. It's a curve and it's a model, and there's a ton of information there. It's a pretty extraordinary data set. You don't often get something that you measure that has so much structure in it. Okay, and when you have so much structure in a model, there's a lot of information there. Okay, how did I get into this? Well, I got into this through, basically being told about all this stuff in my 3rd year as an undergraduate here. And these are some of the characters that influenced me during that period. This is Professor Tom Kibble, who sadly is not with us anymore. And Tom gave me, Tom was running the quantum mechanics course in the 3rd year. And to me, if I can put a finger on the one single course that I remember from my undergraduate year that caused me to be interested in doing research, I'd have to point to Tom's course. He gave a beautiful course on quantum mechanics. Ray Rivers, on the other hand, who's an emeritus professor still in our group, he gave a completely chaotic course on advanced field theory, which basically 20 hours of lectures on path integrals, and it was actually hugely inspiring. This was the first time they ran the 3rd and 4th year advanced courses. In fact, my year was the first one for the students here. It was the first year where the degree was 4 years instead of 3. So this was a completely new ground. And it was, in some sense, completely chaotic, but it was actually wonderful to see this advanced stuff. And Andy Albrecht, another member of the theory group here, who's since moved up back to the States, he taught me cosmology. And it was during that course that this idea, I really hadn't looked at cosmology before. Cosmology was some sort of this dark art where people would sit down and discuss about the Hubble rate being 100 or 50 for hours on end. Hubble had gone on, it was broken, it wasn't working. But it was really taking these courses that it sort of dawned on me that cosmology was sort of a lab where you could actually test fundamental physics. When combining ideas from particle physics, gravity, the theory of gravity, and observations, you could actually start making conclusions about fundamental physics. And that was just an eye-opener. I absolutely loved it. I thought I'd show a picture of myself at the same time. Okay, I didn't look like this, but in research terms, I was a baby compared to these mythical figures that would descend from the research floors and come and give us these amazing lectures. But of course, just looking at that, I think I was already asking the deep questions about cosmology. Andy got me interested in cosmic strings. I don't have time to go into the details of cosmic strings, but there were these wonderful objects that arose. Tom Kibble actually had explained how cosmic strings these topological defects could be formed in the universe. They were wonderful things. I was just absolutely in love with this kind of physics, and the fact that they could exist in the universe just inspired me to look into this. And in fact, I ended up doing a 4th year project with Andy. It was the first time these projects were run. He thought we'd figure out how cosmic strings worked, how they imprinted signals in the CMB. None of that happened, of course, but I learned a load of physics, and it was really interesting. And Andy asked me to carry on and stay on for a PhD. So I went away for the summer, came back, and the first day in, I had a meeting with Andy, and he said, actually, I'm not going to be your supervisor. At the time, he was already planning his move back to the States, so he didn't really want to take me on as a student. But he said, but I have, we've just hired a young Royal Society fellow. He's absolutely fabulous. I think you'll have a great time, and he's going to supervise you. And I went, oh, okay. Who is it? Okay, it was João Maguejo. Laughter from those in the know. Who's here today, one of the amazing characters that have influenced my scientific career. And I ended up doing some wonderful stuff with João to do with cosmic strings. That was the state of the art for visualization at that time. We worked out these networks of strings and how they could have imprinted signal in the CMB. This was a big rival. There was a big rivalry between inflation theory and cosmic strings as the origin of structure in the universe at that time. It was a very interesting period. But to give you a sense of what happened when I was submitting my thesis, this was a central plot to my work. Again, don't worry about the details, but this is that squiggly line with these peaks. João and I had worked out the cosmic strings predicted this kind of curve here. And the rival inflation theory predicted this stuff. These were the data points existing at the time from Kobe. So you could be forgiven for thinking, well, okay, both of these pictures exist. And then a few months before I had to submit my thesis, this happened, which is never a good thing when you're trying to become famous by predicting something extraordinary. An experiment called Boomerang came around and did this amazing thing. It measured the power in the CMB on scales around a degree, and it measured this bump. And I tried, but there was no way I could fit our work with the observations. They just wouldn't work. But actually, going back to this plot, when I looked at it the other day, that wasn't the most amazing thing. The pain of this failure has faded with the years, but the most amazing thing is that we're still plotting this curve with what I called a SCDM, and that was back in the day was the standard cold dark matter model. And another extraordinary thing that happened around that same time was this a very famous result in cosmology, which was that the discovery that today the universe is accelerating. The expansion is accelerating. It's not decelerating like the simplest models in some way, but it's accelerating. And this is the origin. It had been suspected for a number of years before, but these measurements of supernovae, luminosity distances, really underpin this new model that we had to shift to, which was called the lambda CDM model. And what that required was the addition of yet another dark component, which was dark energy, completely unexpectedly. This was it was a bit crazy, right? Why would not one dark component, but two dark components? And at the end of my PhD, I moved to Canada, to the Canadian Institute for Theoretical Astrophysics. And there I met these two characters here, Dick Bond and Lev Kaufman. One crazier than the other. If you have a stereotype of the crazy Mad Hat scientist, these two just fit that profile. Hugely inspiring figures. Lev, who sadly, again, is another character who's not with us anymore. Marco and I, my guest, had a great time for a few years at CEDA with hugely stimulating scientific work. But the main work I did was with Dick, and Dick was an expert on CMB analysis. And he called me up, I still remember, upstairs, and he said that he offered me a job at CETA, and he said, you should come to Canada. I thought, well, why Canada? Canada's a place where you go and trap beavers and shoot polar bears. Apparently, though, Canada was the center of CMB analysis. It's where all the data was going through. And he said, you should come and you'll be able to work on an experiment called Boomerang. And I thought, oh, Boomerang, I know Boomerang. It just ruined my PhD. He said, you'll be able to analyze the data. I said, sure, I'll analyze the data. I'll show it's completely wrong, and I'll save my PhD. Actually, what I said was like, that sounds amazing. When can I start? And so I went off to Canada and worked on the Boomerang data. This is Boomerang, by the way. Boomerang was a telescope on a balloon flown above the South Pole around Antarctica. It flies really high, sort of hundreds of kilometers. Tries to get above the atmosphere because you can see the CMB really well above the atmosphere. The atmosphere it's just a lot harder to see the CMB from the ground. The kind of maps it produced was this. This is a small fraction of the sky. It's about, well, it's a few percent of the sky, just under 10% of the sky. Same thing, hot and cold spots, but now at much higher resolution. Okay, so it's less of the sky because it's not a satellite, it can't see the whole sky, but at much higher resolution. That was one of the big discoveries that came out of the CMB. That structure was used to basically determine that in fact the geometry of space-time is flat, and it's very, very close to flat. That, in addition to that, you need to use some other information from related observations. And the reason you can tell that is because the physics tells you the size of the structure that you should see in the map. Okay, you predict the physical size of that structure. And then you observe it at a certain angular size. Just like if I was holding a ball, you'd be able to figure out, well, you Google it and figure out the standard size of a ball. And then if you measure the angular diameter of that ball, if I was holding it here, you'd be able to accurately measure the distance between me and yourself. And that's exactly what happens with the CMB. And it basically, Boomerang said, well, we live on this curve here. That very special place, that flat place. And this was the data. Again, it's this squiggly curve. I've plotted it in with a slightly different axis. For a long time, all we had was the Kobe point, and the Kobe point was just basically a single point here. And Boomerang measured this peaky structure, measured these harmonics, and it was an incredible achievement. The fact that you're seeing these harmonics has really profound implications for where the structure in the universe comes from. Amazing. And Boomerang actually measured multiple peaks. It measured the harmonics of this sound, of these sound waves. Boomerang has also a special place for me because this was a team on the ice that flew Boomerang in 2003. There was 2 flights of Boomerang. I worked with a number of these characters, formed lasting relationships to the point where, in fact, one of them I dragged back to London with me. I'm not referring to the penguin, although that would have been quite cool. But here she is, Carrie, my wife, who actually built part of Boomerang and was there on the ice to fly it. So some scientific collaborations are more fruitful than others, and I think my kids are a testament to that. Subsequently to that, there was a flurry of activity. These a huge number of experiments from the ground and on balloons measured more and more precisely patches of the CMB. And I was just incredibly lucky to be involved in many of them. I don't have time to go into many of the details to do these experiments credit, but I'll just show you a little combination of how the data evolved in just the space of a few years. And these are experiments I was lucky to work on. And we just basically mapped out the spectrum, a huge amount of information in this plot. And then finally came WMAP. WMAP was a new satellite in 2003 that measured this. So this was the image that we had from Kobe, and then in the early 2000s, WMAP measured this beautiful map here. Again, it had a transformative effect on the field. That was a NASA satellite. And then we had to wait a few more years until very recently for the Planck satellite, which was a European satellite, to be launched and then return this kind of map. You can see how much more detail there is in this map, but of course it's the same on the larger scales. You can still recognize the features of Kobe. but there's, in addition, there's a lot more finer details. And this map, quite simply, without being facetious, this image is one of the greatest achievements of humanity of all time, and I can easily state that. This was a huge effort, both technologically and in human terms. But the idea that us humans can actually predict that this thing should be out there, build instruments to go and measure it, and then it all happens to be exactly as we thought, is just astonishing. Really incredible stuff. In terms of that curve that I keep showing, this peaky thing, this is what the data looks like now. This is amazing, right? Okay, it looks like it's fake. It's like you've gone and drawn dots along the line. That's because the error bars are smaller than the resolution of the data points. Really amazing stuff. And what is it tells us? It tells us that we live in this lambda CDM model, this crazy model. Another aspect of discovery that happened at the time was polarization. I don't really have time to go into it, but polarization was one of the discoveries that had been one of the aspects of the CMB that had been predicted, and we discovered it. It was there, and it was there exactly as predicted, and I was involved in two of the experiments that actually returned some of the first maps in the early 2000s. Polarization holds some key information about this epoch of inflation. Remember, we live in a universe now that seems to have undergone an early epoch of acceleration and also a late one. The universe is accelerating now. So acceleration is this funny thing that seems to keep happening in the universe. And polarization holds some key information about this early epoch of acceleration, this inflationary period. The other thing that Planck returned is a beautiful map of this polarization, of course. So this is a single frequency of Planck. The galaxy is still there. You haven't fit it out because it's the raw map at a single frequency. I think it's 143 gigahertz. And you can, if you're polarization sensitive, you can construct this beautiful map where the color is now the polarization fraction of the light you're observing in each direction, and the lines tell you which direction the polarization is in, the linear polarization of the light. It's a beautiful map. This we call the Van Gogh map. It's a sort of impressionistic map. As an expert who's trying to discover things about inflation, this map is the scariest thing I've ever seen, because you can see that most of the stuff you see in there is galaxy. It's a foreground. It's stuff that we want to see through. And only in the highest galactic latitudes is the signal of the galaxy not completely obvious. So all this has had a transformative effect. When you ask a cosmologist, remember, what is the universe? What's happening to it? What is it full of? They'll stick up a thing like this, right? Which is a bunch of numbers. These are parameters in our model that define this lambda CDM model. Don't worry about what they mean, but look at the numbers, okay? It's a number plus or minus an error. It's extraordinary, okay? If you ask me how much baryons are there, how much matter in the form of baryons in the universe, I'll go, oh, in some funny unit it says 0.2225 plus or minus 0.00016, okay? That's an extraordinary thing, okay? Sub% level accuracy on the parameters that make up this model. It's as if you were staring at something and measuring it in the lab, okay? It's that sort of level of accuracy. And what it tells us is this funny lambda CDM picture. We know very precisely what form of matter matter and energy is in the form of dark matter, dark energy, baryons, the standard model, and photons. Great, right? We know this incredibly precisely. However, right, over 95% of the stuff that fills the universe is dark, right, in one form or another, dark matter or dark energy. That's incredibly strange. Just jumping forward to the most recent things, what do I do now? What's the next frontier? The next frontier is B modes, and it's that signal I mentioned, that very particular signal in the polarization of CMB that has to do with this early epoch of inflation. It's incredibly faint. The light is polarized around the 10% level, and then go down a few orders of magnitude again, and that's the signal you're looking for. And you're looking for particular patterns in the polarization of light. Maps like this tell you how the light is polarized, and you're looking for a very specific kind of pattern. What that pattern tells you is something about gravitational waves. That was a huge news story this year, of course, the direct detection of gravitational waves earlier this year. Okay, and those are coming from stuff happening with black holes and spiraling and emitting gravitational waves at large distances. What we're going after is what we call primordial gravitational waves that would, well, if we measure them, they would have a profound impact on our understanding of that early acceleration phase. And it would be a huge discovery, which apparently happened a couple of years ago. This was a famous BICEP result that announced that they'd in fact measured this signal. Huge headlines around the world, a bunch of beaming people that had basically a Nobel medal in their pocket. Unfortunately, it turned out to be wrong. What they had seen was this thing, which is this very scary thing, which is basically the signal coming from the galaxy, which confuses the stuff that we're actually going after. And I'll just sort of give you a brief idea of what I do currently in this search for B modes. Currently working on another balloon-borne experiment, another balloon-borne telescope called SPIDER, again led by Princeton and Caltech. And this is actually going after that signal. It's amazingly difficult. This is really difficult stuff. To give you an idea, these balloon flights happen, and they happen. They're up there for a few, sort of on the order of 20 days, 2 weeks, 20 days, and they take data. And they fill a hard drive with data. And from that data, you want to make a map. To make this kind of map here, which is the current SPIDER map that we're working on, this is unpublished work, it's what we're working on right now, has taken nearly 2 years of work. And that's quite typical in these experiments. You collect data, it takes about 2 or 3 years before you can actually publish the result. So I'm just going to finish off by just with a brief summary. I've given you hopefully an idea of really interesting developments that have happened, tied into my own career in this field of cosmology, and in particular in the measurement, analysis, and predictions involved in the cosmic microwave background. The picture that has emerged over the past 20 years is a really weird one. Okay, we've got really fundamental questions. We're facing fundamental questions. We're just facing them with incredibly precise results now. We're in what I call the post-precision era of cosmology, because we have the precision, but we need to really figure out what's going on. What is all this dark stuff? Okay, dark energy and dark matter, very, very difficult to understand. We have very simple phenomenological models for what they are and how they control the evolution of the universe, but we don't have any fundamental, truly physical understanding of their nature. Why did the universe undergo these 2 periods of acceleration? Very strange. Why is it accelerating today? You know, why is this dark energy around? Very fine-tuned models. You need to explain this thing. Is this a sign? Is this all pointing to that we need new physics? You know, is it new gravity models? Is it in the particle physics models, or maybe both? Okay, and of course, this is a huge area of activity, particularly upstairs in the various groups here at Imperial. And the thing I can say, with the experience of 20 years working in this field, is that the only certainty is that there will be really many more interesting discoveries to come and huge surprises. So I'll stop there. Thanks.
Let me introduce Professor Marco Peloso from the University of Minnesota, who's going to give the vote of thanks.
Okay, good evening. So first of all, I come from US. I left 1 month ago. I gave a kiss to my daughter saying, we're going to get the first woman president. The world is great. And here we are. So I'm considering sticking around for 4 more years, if you don't mind. Of course, here you don't have examples of bad votes, right, or crazy politicians. So, so I'm very happy. Going to the business, right, I know Carlo for almost 15 years. We were together postdocs in Toronto. And as soon as I arrived there, I wanted to look for people who were good and nice, which is hard to find both. And Carlo was really one of them, and it was a great pleasure, and we've been working together since then. Carlo is someone who can both do theory and analyze data, which is something quite remarkable. He showed us pretty pictures, right, really beautiful, but you have to imagine how hard it is to analyze these pictures, right? There is a 10 micron Kelvin or micron Kelvin. This is completely crazy how you can analyze it. And imagine that there is atmosphere, there is galaxies, there is stars, there is dust, and people need to get to that precision, and they spend years working on that. Carlos showed us the example of BICEP, right? And when the BICEP paper came out, I read it, as all of us, immediately, and I saw that they were using 7 methods to clean the data. You know, when they use 7 methods to clean the data, you worry that none of them is going to be right? But what I noticed is that 2 methods were by Carlo. So I immediately called Carlo, and I said, oh, Carlo, that's great. They use your method. It must be right. And Carlo told me, no, they didn't use them well. They should have just given me a call, and I would have explained them. So this incident shows 2 things. First of all, that Carlo is very well known, very well respected, and these guys would have all got the Nobel Prize. Okay, they were in 4, so they should have killed 1, but they would have got the Nobel Prize. And they were using Carlo's method because it's well known that he knows how to do this stuff. But then these things are so hard that if you're not Carlo, it's harder, in a sense. So it's really quite impressive, this. And I could give you other examples, but since I'm being recorded, I don't want to make too many enemies. But, but I really want to say, right, that these are very difficult stuff, and the pictures are beautiful, but there is a lot of work behind them. So on more personal ground, Carlo is a true British hero. He's really, you know, we saw here he's from Imperial, but he's really a true British hero. He's the only person I know who gave up Italian citizenship. No, everyone thinks, oh, it's great, you're Italian. So it turned out that I was not the only one who wanted to work with Carlo. Also, the Italian army wanted to work with Carlo. And, you know, Italian bureaucracy is such a level that they kept pestering him, and he decided, okay, I give up, I'm British, I don't care. And so, essentially, he did Brexit on his own 10 years before everyone else. So you can really see, right? And on a personal level, he's really one of my heroes, essentially. He has some qualities which are clear to us. You look at his beautiful daughters, you look at his family, you know he's a great father and a great husband, and that you can see. But then there are some qualities that if you don't really know him, you don't know them. And most of us, there are many people here who are physicists, and if you're not in physics, I tell you physics is hard. I mean, maybe you didn't know, but it's quite hard. And while it's very funny to be a physicist, it's very hard to become a physicist. And when I was a PhD student, I must tell you my social life touched a deep, a very minimum. And I was essentially sleeping in all my spare time, either watching TV or sleeping. Now, in a spare time, Carlo became a Royal Marine. So imagine, right, you're doing PhD in physics, and when you go home, you go train for the Royal Army. So that's how he is, right? So full of energy. He's a pilot. He drives airplanes. So one day he brought me with him, and we were in the middle of the air, and he told me, okay, Marco, now you take over. Now, this was the hardest minute of my life. So imagine how you know that if you don't do nothing, you survive, right? So how hard it is for a minute not to do anything. At some point I told you, okay, you take it back. It was really, really hard. Of course, he sails boats, right, obviously. If you fly planes, you also sail boats, obviously. And something that really annoyed me a lot is one day I went to his house, and he had beautiful drawings on the walls. And I said, oh, very nice. Where did you buy them? Oh, no, I just drew them myself. I said, okay, that's too much. So I'm not really good at piloting, drawing. I think I'm good at judging people. And I consider Carlo one of my best collaborators and a great friend. Okay, thank you.